let's look, we're coming towards the end of the lecture now, or the main part of the lecture, and we can look at the last part that's particularly related to Git in GIS, and that's the structure, how the data looks, so to speak. I've mentioned the concept of raster and vector, and I mentioned the thing with triangulated irregular networks. And there's a connection between these, this structure that is, it relates to whether it's discrete or continuous, but it's not concrete. It doesn't have to be that way. So what do we mean? Well, raster is like an image, a series of pixels or cells. When you take a photograph with your camera, you end up with a raster. That's what it is. The thing you're looking at on the screen now is actually a raster. It's a series of pixels. And the computer, it stores everything in a discrete manner. But we're saying here that raster does not represent discrete data efficiently. But that's exactly what it is. It is discrete data. But actually, if we have truly discrete data, if we can conceptualize the data as being discrete, we can represent it more efficiently as a vector quite often. Whereas the vector format, we're going to look at this later on, tends not to be able to represent continuous data efficiently. The TIN is an attempt at this. The triangulated irregular network is an attempt at storing continuous data in a vector format. So a TIN consists of a series of triangles, and across one triangle, across one face of the TIN, we can interpolate a value. Wherever we want across that face, we can interpolate a value. So it becomes continuous in that sense. And the only thing that we've stored are the 3 points and the connections between them, describing them as being parts of a triangle. So that is one way of storing continuous data as a vector. It works and it's quite popular, but more commonly for continuous data, such as an image where we have light continuously varying in its strength across the image, we would prefer to store it as a raster. And again, this comes back to this thing that actually it is being stored as discrete data, but we've zoomed out far enough so that it looks continuous to us. Now, the reason for this, why we have this problem where raster actually describes data, continuous data, more efficiently, is because we've chosen that zoom out level, and because the raster will always have to store data in every single pixel or cell. Across that whole of the image, there is a piece of information in every single pixel, regardless of whether something has happened or not. 2 pixels next to each other can look exactly the same, but you can't, there's no efficient way, I mean, unless we do compressing the data, but generally speaking, what we're talking about is we have to store the information again. This pixel looks the same as that one, which looks the same as that one, which looks the same as that one, which looks the same as that one. That's not terribly effective, but we have to do that. That is the nature of the raster, how the data is stored. Whereas with the vector, once we have that continuous, once we have, sorry, that package of data where everything's homogeneous, and we could actually just say, well, across this whole area, that's all the same thing. That's one discrete package of thing. Well, we could just draw a line around it and say, oh, and call it a vector. All of that, we don't need to worry about what's happening inside because it's all homogeneous. We don't need to describe every single step. We just say that there, all one and the same thing. So this is why we say that vectors are better at storing discrete data and rasters are better at storing continuous data. But both are capable of storing discrete, and both are capable of storing continuous data. It's just how efficiently they do it, and whether it's the best practice for what you want to do. And it might vary depending on what you intend to do with the data. If you want to perform some sort of processing or run an algorithm on the data, you might need to change from raster to vector or vector to raster. So that can happen as well. It's not that you shouldn't do it, that you can't do it. It's just what is best practice, what is more efficient. So let's look at this This is a raster. If that wasn't particularly clear, we have a picture. This is just a picture, and it covers this entire area, and in every single place there is a pixel. And now this is continuous data, so we can see the colors varying continuously. Now we've zoomed in too far, so they now look like discrete packages. But when we're out here, we can just see continually varying colors. We might see in places very sudden changes, but it's still a continually varying surface where colors vary constantly. Now we could, of course, so we've got this, the data has been stored in this manner, because that's the nature of a computer, it has to store these discrete packages. But when we zoomed out, it looks continuous. But we can describe these things. I don't know if you can see what this is. It's a trampoline. Somebody's garden has been used to put a trampoline in. But if we then interpret that information and describe it as a bunch of things, why did I bring up the trampoline? Well, we could describe that as a thing. When we looked here, it was a collection of pixels, and we could interpret using our brains to say, well, this is the edge of something, and this is the center of it, and actually it's a trampoline, and we can describe that as an object. We don't actually need to have all of these pixels with their varying colors. The only relevant thing here is it's a trampoline. So let's draw a circle and say, right, in this place there's a trampoline. All we need to do is have the information about a central point and the radius, and then the fact that it is a trampoline, rather than it's a bit grey here, lighter grey there, even lighter grey there, slightly darker grey there, That's a lot of unnecessary information just to say it's a trampoline. Our brains are doing a lot of interpreting there. So we convert all of these things into all of this continuous information and we call it in things. We say objects exist. They are homogeneous across their entirety, but they exist as things. And this allows us to connect an object, say this object here, we connect that object, whatever that is, with this description, the outline of this polygon is connected to a line in a database, for example, in a GIS it is, where we can store lots of different types of information. We don't have to store this information. It could be a lot smaller. We can miss out some bits if we want, but we can put in all of this other information that is not is not continuous. It's all discrete bits of information, names of different stuff occurring across the entirety of that thing, that thing that is a vector object here. So this is an important distinction. If we were to store the previous photograph as vectors, describe a little square, and then say it has this color, and then describe a little square, and it has this color, and describe a little square, and it has this color, that will become very inefficient. So we can store it as a raster. Why rasters are more efficient at doing that, we'll come to in a later lecture. But when we have a generalization of an entire area, we don't need to know about the colors there or whatever continuous qualities there might exist varying across the entire surface. We can just say that is all one thing. It's a thing, it exists, and it has this distinct boundary. Within that, all of these qualities apply. They are all equally valid across the entirety of that surface. These are important concepts for the vector. And then when we look at the triangulated irregular network, we can see these triangles I was talking about. We store data at a point there, a point there, and a point there, and we say those three belong together, and we can mathematically linearly interpolate a value anywhere in that triangle, and it will be some combination of these 3 points. Again, these 3 points here, any point within that face we can find a value for by linearly interpolating between these three. And that gives us our continuous surface from a vector that is reasonably efficient to store, because we only need to store the information on that point, that point, that point, that point, and their connections. We don't need to store information about what's existing in between. So it is a very popular format for storing typically elevation data. Now, in the course you will have lectures on vectors and rasters, lectures on each of those. We won't really be looking at triangulated irregular networks again on this course. They will come up in a later course. And this is just an example of what they may look like.